Hello and welcome. Today, we're diving deep into a super important chapter in chemistry, ionic equilibria. If you've ever wondered what's really going on inside a solution when a reaction happens, well, this is where we find the answers. It's all about the incredible dynamic dance of ions in water. So let's get right into it. So here's our game plan for today. First, we're going to meet the main players, the electrolytes. Then we'll get into the rules that they all play by. After that, we'll talk about measurements, the whole pH scale, and then the control system of buffer solutions. And we'll wrap it all up with the final act, the drama of precipitation. It's a full story from beginning to end. All right, let's meet the stars of our show, electrolytes. It's a simple idea, really. These are just substances that, when you dissolve them in water, break up into ions. And it's these little charged particles that get all the action going and allow the solution to do things like conduct electricity. They are the reason we're here today. Now, here's the thing. Not all electrolytes are created equal. You've got your strong electrolytes, like hydrochloric acid. You drop them in water and bam, they ionize almost 100%. The key thing to see here is that single arrow in the reaction. It's a one-way trip. But then you have weak electrolytes, like the acetic acid you find in vinegar. They only dissociate a little bit. And that double arrow, that is so important. It means you've got an equilibrium. It's a two-way street, with the reaction happening in both directions at the same time. Okay, so if a weak electrolyte only breaks apart a little, how do we measure how little? Well, that's where this little Greek letter alpha comes in. It's called the degree of dissociation. Just think of it like a percentage. It tells us exactly what fraction of the total stuff has actually split into ions once everything settles down at equilibrium. It's a super simple but really powerful way to measure weakness. Right, so we know weak electrolytes don't go all the way. The next big question is, can we actually predict how much they'll dissociate? And the answer is a big yes. The rulebook for doing this is a really important idea called Ostwald's dilution law. Okay, so for any weak acid, we'll just call it HA for short, we can set up something called an acid dissociation constant, or Ka. This formula, it's just a ratio, that's all it is. It's comparing the concentration of the products, the ions that have broken apart, on top, to the concentration of the reactant, the acid that's still whole on the bottom. Long story short, a bigger Ka means you have more ions, which means it's a stronger acid. Simple as that. And here is where Ostwald's law becomes your best friend, especially in exams. For most of these weak guys, alpha is so small that we can use this awesome shortcut. The law just boils down to this. Ka is approximately alpha squared times C, the concentration. This little formula is an absolute powerhouse for solving problems because it makes the math way easier. And one of the coolest things about chemistry is how symmetrical it can be. The exact same logic we just used for weak acids, it applies perfectly to weak bases. We just swap out Ka for Kb, the base dissociation constant, but the formula looks exactly the same. Kb is about alpha squared times concentration. So hey, if you get one, you totally get the other. So we've been talking all about the strength of acids and bases, but how do we actually measure this in a consistent way? Well, the answer, believe it or not, comes from the most common liquid there is, water. Yep, pure water is actually a super weak electrolyte, and it's water's own special properties that give us the entire pH scale. See, water has this really neat trick called self-ionization. Basically, one water molecule can pass a proton to another one, and you end up with a hydronium ion and a hydroxide ion. Now, if you multiply the concentrations of these two ions together, you always get a constant value. We call that the ionic product of water, or Kw. It's a fundamental truth about water. And here it is. This is the number you've got to remember. At 25 degrees Celsius, which is about room temperature, Kw is always 1.0 times 10 to the minus 14. This one constant value is the absolute bedrock of the entire pH scale. It's kind of like the magic number for this whole chapter. Now, working with tiny numbers like 10 to the minus 7 is, well, it's a pain. So to make life easier, scientists came up with the pH scale. It's a logarithmic scale that turns these awkward little numbers into a nice, friendly range, usually from 0 to 14. And the P in pH, it just means take the negative log of. So pH literally means the negative log of the hydrogen ion concentration. That's it. And just like pH gives us an easy way to talk about acid levels, pOH does the exact same thing for base levels. It's the same logic, 100%. pOH is just the negative log of the hydroxide ion concentration. It's the other side of the same coin. This brings us to a beautifully simple and seriously powerful relationship. At room temperature, in any water-based solution, the pH and the pOH will always add up to 14. This is maybe the most important takeaway here. It means if you know the pH, you automatically know the pOH, and vice versa. They're locked together. Okay, now imagine a solution where you could add a bit of strong acid or a bit of strong base, and the pH barely even moves. It sounds like magic, right? Well, it's not magic, it's buffer solutions. These things are like the pH shock absorbers of the chemical world, designed to resist any big changes in pH. So buffers usually come in two main flavors. You have acidic buffers, which are a mix of a weak acid and its salt, and you have basic buffers, which are a mix of a weak base and its salt. The secret ingredient is that combination, the weak thing and its salt partner. They work together like a team to gobble up any extra acid or base you add, keeping the pH rock solid. So how can you figure out the exact pH of one of these amazing buffer solutions? For that, we've got a fantastic tool, the Henderson-Hasselbalch equation. This formula lets you calculate the pH of an acidic buffer directly, just by knowing the pKa of the weak acid and the ratio of the salt to the acid. It's basically the instruction manual for buffers. And guess what? For basic buffers, there's another version. And just look at that perfect parallel structure. Instead of pH from pKa, you're calculating pOH from pKb, using the salt-to-base ratio. The logic is 100% identical, which makes it super easy to remember and use both of them. Okay, we've made it to the final act of our story. So far, all of our ions have been swimming around happily in the solution. But what happens when the solution gets too crowded? At what point do those dissolved ions decide, you know what, let's get together and form a solid? This is the grand finale of ionic equilibria, precipitation. Now, to really get precipitation, we need to know two key terms. First up is the solubility product, KSP. Think of KSP as the solution's absolute maximum capacity. It's the limit. Then you have the ionic product, or IP. Think of this as the current amount of ions in the solution at any given moment. So KSP is the limit, and IP is where you are right now. This table explains the whole game. It's just a constant battle between IP, the current state, and KSP, the maximum capacity. If your IP is less than KSP, no problem, you're unsaturated. More can even dissolve. If IP is exactly equal to KSP, you're saturated, perfectly full. But if your IP becomes greater than KSP, the system is overloaded, it's supersaturated, and a solid has no choice but to form. So here's the bottom line, the crucial point. The second that the ionic product, IP, gets bigger than the solubility product, KSP, that solution is unstable. The system has to fix itself, and fast. The extra ions will literally crash out of the solution, forming a solid precipitate. And this keeps happening until the IP comes back down to the KSP value and that beautiful equilibrium is restored. So when you look back at everything we've talked about, what's the one theme that ties it all together? It's equilibrium, right? Whether we're talking about a weak acid, or water itself, or a buffer, or salt precipitating, it is all about the system trying to find this perfect, dynamic balance where the forward and reverse reactions are happening at the exact same speed. And after all this, I want to leave you with one last thing to think about. How do these rules actually affect our real lives? I mean, think about the medicines you take, which have to dissolve just right to work, or the quality of the water you drink every day, or maybe the most amazing example, the super delicate pH balance in your own blood, which is kept stable by buffer systems. This stuff isn't just in a textbook. It is everywhere, and it's inside of us. Pretty cool to think about, isn't it?